All right. Good morning, everybody. Happy Wednesday. Hopefully you had a nice long weekend with Labor Day weekend last week. Um, so I guess one update is for code grade. For some reason, I had several students who weren't able to upload their assignments actually after midnight last night, which is kind of interesting. Thank you. Really, I don't know why it locked for certain people because I had it where it was due Tuesday midnight, but it locks Wednesday midnight. So I'm not sure what's going on over there, but I guess you can send me your code and I can just see if I can just manually grade that or if I have to upload that myself to code grade on your behalf. I'm not really sure um, how how that works on code grade, but anyway, yeah, it's pretty much the only announcement there. Um, I'm gonna say homework number two. I believe that's due next Monday. So anyway, in that one, there's more than one possible solution, I believe, for the word ladder. So we'll have to unfortunately, code grade might not be perfect in that regard. So we'll have to find a way to deal with that. So we can actually add points manually to the auto grade part. So we'll have to just sort of see that. So I mean, yeah, that one will be a little bit of an interesting one. So I think for the most part, most of the assignments won't be like that, where there'll be only one answer, but that's the only one I can see for right now where there will be more than one possible solution. So anyway, there's that. So let's go ahead and sort of recap a bit from way back from last week when we had class last time. So let's begin the screen share. Okay, so this was the last thing we covered, which was searching. So we had linear search, we had binary search. So linear search was really just we simply go through every element one by one until we find our search value. So S was the search value, N is the size of the array, A was the array. So that's really all there is to linear search. And we went over that it's going to take O of N in the worst case because in the worst case scenario, the S value either is not in the list at all or happens to be at the end of the list, or if it's somewhere in the fractions, let's say in the halfway point or 3/4 point or somewhere around there, it's a fraction of n still. So in the worst case and also the average case, it'll be something linear. It'll be a fraction of a linear sort of runtime. So linear search, which makes sense, it's O of n. Then we had this binary search algorithm, which actually takes O of log n time because we constantly break the sort of the range in half every single time. So initially, we have the entire range as our where the S value could possibly be. And then we constantly cut that range in half every time. So I believe it's supposed to be that M value is supposed to be actually, I think, L plus R divided by 2 plus L is the actual real value. But the idea is we sort of find a midpoint between L and R is really the idea for this M index. So we constantly break it in half. So we always check the middle element to see if it equals S. If it doesn't, then we sort of decrease that range. So we shift L up to the midpoint or R to the midpoint. So every time we sort of shrink that range in half every single time until eventually either we find the element S, or until once R is less than L, that means we tried every single possibility and we couldn't find sort of S value. Because at a certain point, in the worst possible case, L and R will be the same value, same element, and we're going to have only one element left over. And that element has to contain S. If it's not there either, that means we know that, well, we narrowed our search down to one element. It still wasn't there. That means S can't be in this list. So we constantly break this list in half every single time until we finally either find S or we don't find S. So that behavior is definitely logarithmic. We divide by 2 every single time. So it's log 2 of n or O of log n. So then, okay. So let's to summarize these two searches. What's what's the best one to use all the time, or what's the difference, or how do we really know which one to use, really? So let's go ahead and just do some sort of more notes here and just do some sort of wrap up of these two algorithms. So basically, um, So if the list, let's go ahead and actually do a compare and contrast with linear search and binary search. So I'll have linear search over here, and I guess binary search will be on this side. Okay, so linear search, I guess one benefit is that it works for an unsorted list. And works for a sorted list. So it has sort of benefit that will work for both. So the runtime for linear search, if it's unsorted, takes O of n, correct? What if the list is sorted? What's the runtime for linear search? Is it better than O of n if it's sorted? And I have the answer there, it's O of n and the same, which is correct because whether it's sorted or not, it does not matter because it has to go through every element. So worst case scenario is a sorted list and the biggest element we're trying to find, which means you have to go through the entire list. So it's O of n no matter what. So it's O of n whether it's O of n whether you're in sort of sorted unsorted. So it's going to be O of n for sorted or unsorted. So anyway, that's sort of the deal there. Binary search, it works for a sorted list only, which will give us O of log n in that scenario. And it does not work for unsorted. So a kind of a sort of a trick question possibly on the exam could be something like, oh, if it's unsorted, then binary search runs in worse than log n time, which is not really correct. It doesn't work if it's unsorted because remember how binary search works. It checks the middle, and let's say if the middle element is less than our search element, then it must be on the right side, and it will keep searching there. But if it's unsorted, you can't make that assumption that your search element has to be on the right side. If let's say S value is larger than A index M, you can't make the assumption that the right element will be somewhere on the right side. It could be on the left side as well. So it will not work at all if it's unsorted. So really, if it's a sorted list, if you're given a sorted list, you might as well use binary search because it'll be faster. If it's unsorted, you have no choice but to use a linear search. Now, one last sort of piece of info to wrap up this is we have two conditions. So what if I want to search for one search for element in an unsorted list. Now let's say if I want to do just only one search. Just one search on unsorted list. Then what's the better algorithm to actually use? Well, let's go ahead and highlight these two. So for linear search, it would just be O of n for that one search. If you want to do binary search in this scenario, which I guess I'll sort of put this, maybe actually I can put it to the next, I can put it side by side, I believe. I think I can. So for binary search, we first have to sort the array. So we first have to do, a sorting procedure. So first you have to do a runtime for sorting, which we don't know what this is yet. We'll have a proof of what's the runtime for sorting, but for now we'll leave this kind of open. So runtime for sorting, first sort the list, and then plus O of log n. So the real issue here is what's the runtime for sorting? If it takes um, n time to sort, then there's no real benefit of linear search over binary search. If it takes less than n time, which seems to be almost impossible, then this binary search is a better approach. Now, if sorting takes more than n time, then the binary search version is actually going to be worse for this scenario because sorting is a very expensive operation. So you sort first, then we do a search. Well, there's no real benefit possibly there. It's almost like the highway. Let's say to get onto the highway takes a little extra time, but then you gain time by going faster than the regular surface street speed limit. But if you're only going to the grocery store next down the street, you're going on a highway to get there. It's kind of an overkill. You might as well just take the service street and go straight to the grocery store. So you really want to use this binary search if it's already sorted, or if you have to do many searches. So what if I say you have to do m searches? So we have this scenario. So m, which will be, I guess m, will be larger than or equal to n. So n is your array size. You're going to do m. So you do many searches, basically. Then what's the compare and contrast of these two? Well, linear search approach, we have to do m number linear searches. The runtime will be O of m n, I guess, because we do linear search, which takes O of n time, m number of times, so it'll be mn runtime, because we do m number of linear searches. For a binary search, however, once again, we have to first sort the array, which has its own runtime, plus we do m number of binary searches in this case. So if you do many searches, then is it worth it to first sort the array and then, do m number of searches? Well, in this case, it might be worth it, because think of n number of searches as if you're going really far away, then maybe the highway, so let's say from your house to get onto the highway, it takes a bit more time, but you save a lot of time afterwards because you can go much faster than 45 miles an hour. You should definitely go only 65 miles an hour on the highway, never any faster, which, nobody ever really maintains that. But you go faster than 45 on the highway, I'm guessing, or probably faster than 65 as well. But anyway, though, the idea is that it might take a little overhead to get onto the highway. Once you're on, though, you're going very fast. If you have to go very far, then this approach is better. So if you do many searches, it's actually worth it to first sort the array and then do m number of binary searches. If you have to do only one search, then really sorting the array first just for one binary search actually is going to be more cost heavier. So it's better to use linear search in this case. But it depends on what's the runtime for sorting, which we'll kind of go over that whole concept later on. So, well, I guess if m, well, let me see, if m equals n, or a fraction of n, let's say if m equals n over 2, then it might still be better. So as long as m is not some very small constant, if it's somewhere around a fraction of n or larger than n, then it's okay. But if m is some small constant, then it's going to be not worth it. So m can be less than n, but it must be a fraction of n of some sort to be worth it, really, to use this sort the array first and then do binary search m number of times. Yep. So we'll kind of, prove or go over what's the real runtime for sorting. But for now, we're going to go over several different sorting algorithms, I guess, since we've covered searching. So let's go ahead and cover sorting at this point. Let's go ahead and just, begin sorting. So let's start with our first one, insertion sort. Now, sorting is a very celebrated sort of concept. It's one of those really the most simplest complicated problems in computer science. So back when I was younger, I had a friend who was a bio major. Now, I'm not saying anything about bio majors. I mean, biology is a pretty cool, major to do. I mean, I really don't, I guess I didn't choose biology, but it's not a bad major. It's a really interesting topic. But I told this person that, yeah, sorting is one of those really cool, very simple, complicated problems in computer science. And then she tells me, well, why? Because sorting, you just sort of move elements around and it sorts, right? Well, the idea is that I don't talk to this person anymore, and it's not really because, actually, no, it's because of that topic, because of sorting. That's the reason why I don't talk to this person anymore. But the idea is that it's just that people who aren't really in CS, they might not really know what's the real sort of what's so important about sorting. Because okay, fine, you can just sort the elements, just randomly, just move them around, and that's it, easy peasy. Okay, fine. Yes. So, okay. But the idea is that um, what if you have a very big array? Let's say size 100 or size 1,000. Then doing that, what that person suggested, just sort of moving elements around randomly, is that a good idea anymore? And the issue is maybe not so good because n can get very large. So the idea is we want to have an algorithm that can sort an array quickly. So for example, bubble sort works pretty well on small size arrays. But we have, let's say, about 1 million elements in an array. The bubble sort takes about, a half hour of time to actually sort, where a better algorithm can take half a second to sort 1 million size array. So having an algorithm that can do this faster is important because the whole idea of algorithms in computer science is to be able to handle big data sets because n is always going to be a big value. If you only have to sort 10 elements, then there's really no point of CS302 and there's no point of computers. The whole purpose is we can handle big amounts of data and we want to quickly run through them all. So the first we're going to start with will be insertion sort. So let's go ahead and I'm going to just sort of show the code here. So I Googled this, so geeksforgeeks.com has a page on insertion sort. So there's our insertion sort code. So we have this nested loop structure. We have this for loop on the outside and a while loop on the inside. So basically what's going on here is that the inner loop, that while loop right there, what we're doing is essentially this. So this array from index 0 to I minus 1 is always going to be part of our sorted array. So let me go ahead and actually first write some notes here and then I'll go back to the code. So we have this inner and outer loop. So insertion sort is going to maintain a sorted list within the list, within the original list, I guess you can say. So going back to the code here for a second, I starts off at 1. So basically from 0 to I minus 1, the list will always be sorted. So throughout the whole duration of insertion sort, so throughout the execution of insertion sort, elements 0 to I minus 1 will be sorted, and then the elements from I to n minus 1 is part of the unsorted list, or that's going to be the part we're going to try to sort. So the outer loop portion runs the inner loop, and the inner loop, what the inner loop essentially does is it makes room. So essentially, so we know that from element 0 to I minus 1, it's going to be sorted. So element at index I needs to be inserted into its correct position in the sorted list. So the inner loop, the inner loop is going to make room for element I. And then we run this inner loop n number of times. So the outer loop basically just goes from 1 to less than n, so actually runs n minus 1 number of times, which is basically just as good as n, essentially. And the inner loop right here, it's simply, when we do ARR plus 1 equals ARRJ, it's simply just moving an element over to the right. It is shifting elements over by 1 to the right to make room for this key element, which key is going to be the element at index I. It's just going to make room for the key to insert it into the correct position. So once j is -1, we're going to stop. And then once the once the key is larger than ARR index j, we also stop. So one of those two conditions has to happen. So once j is -1, inner loop will stop. If the key is bigger than ARRJ, it also stops. So I guess while both of these are true, if one of these two are false, it will stop. And while these are both true, it's going to just keep on moving elements over to the right by 1, to make room for the key to be inserted into the correct position. That's really all insertion sort does. So, I mean, of course, I can talk about it right here some more, but I think maybe having an example will kind of help us out with how this actually works. So n stands for the size of the array. So n always stands for the input size. Yep. So until we go into graph theory, until then, n will always just represent the input size. So that's sort of the universal. I don't know why n became that variable they used, but n just became that variable essentially. So there we go. So let's go ahead and run insertion sort on an array just to see how it works. This will give us a good idea of what's really sort of what is insertion sort essentially. Because I have some notes there, but those notes might not be really helpful until we begin actually tracing it. So let's go ahead and create a list. Maybe I'll do a list of size 7 or 8. So let's go ahead and do this. So 3, 7, 5, 2, 6, 4, 1, and then I'll just pick 8. 1, 2, 3, 4, 5, 6. Okay, 8 elements. That's good. Okay. See a question there? Yeah, so selection sort is kind of, in a way, sort of similar to insertion sort, but insertion sort's a bit more efficient, or can be more efficient than selection sort, but the idea is the same, is that we're having elements sort of from I, not really, so some counter to n, the n part is a sorted list that we're kind of one by one building up. So that is sort of the idea for selection sort. So for, I guess, our I counter, if you will, so from I to n minus 1 is sorted, and from 0 to I is going to be unsorted list. So, oh wait, so you meant to say insertion sort. So the first half of the list will be sorted actually in insertion sort, and the second part, so from index 0 to I minus 1 will be sorted, and then from I to n minus 1 will be unsorted. Those are elements we're going to just one by one insert into the sorted sort of sub-array, which we'll see the example right here, but that's the idea. So we first start with the following sort of Yeah, I mean, they are kind of similar, insertion and such, and sort of a little similar, but there's some differences in terms of some of the runtimes. But anyway, for right now, we start with this. The index, the first element we're going to assume is already sorted. And I guess you can't really disprove me because if you only have one element, then it has to be sorted. So we start with that where first element is already sorted. So fantastic, we're already kind of good there. So now I is going to be 1. We start from 1. So elements from 0 to I minus 1, so from element 0 to 0 is sorted. So we are actually correct. So that part is good. So now we're going to have to set this j counter. So j is going to be set to the value 0 because in the inner loop, or sorry, with the insertion sort loop, let's go to the code for a second. We set j equals I minus 1. So that means that's where j is going to stand. An inner loop portion will keep on running either until j is -1 or until the key value, which in this case, the key is going to contain 7. The key is always going to be the array at index I, and index 1 contains 7. So we're going to just store 7 into the key, and I'll run this inner loop. So the first check, is j -1? Well, it's not. And is the key bigger than the element at index j? And actually it is, because 7 is actually bigger than 3, so we're done. So the inner loop already finished. That was a very simple case. So what happens here is after we're done with the inner loop, what's going to happen is, well, we're going to set ARR j plus 1 equal to the key. So j is 0, 0 plus 1 is index 1. We're going to reassign this to whatever's stored in the key. And then the result will be the following. So nothing really happened. That was a very simple example, but you know, that's the first step of insertion sort. 5, 2, 6, 4, 1, 8. So now these two elements are now sorted. So what happens is now I is going to be, well, it was 1, now it's going to be 2. So if elements from 0 to I minus 1 are sorted, so elements 0 and 1, those two elements in this array in that green box, is our sorted array. So essentially, 1 by 1, that green box gets one element bigger every single time. It's growing 1 by 1 until eventually the entire list becomes one green box, and that's when we know it's sorted. But right now we can see here the entire list is not sorted, so we have to keep on running. So I is now going to be 2, so j will be set to I minus 1, or in this case, just 1. And the key is going to be the value at index I. Well, I contains value 2, so index 2 contains 5, so the key is going to be 5. So we have to find, well, where does 5 have to go into the sorted list? So looking at this right here, we can see that between 3 and 7 is where 5 would have to go. Let's go ahead and see how this code would work. So the inner loop portion will now go ahead and run. So you first check. So is j -1? Well, it's not. And is the element, is key larger than the element at index j? Well, index j element is 7 and key is not larger, so the inner loop is going to run. The inner loop, what does inner loop actually do? It will assign j plus 1 with element index j. So it's going to basically take this value of whatever is at j, index 1, is going to assign this into j plus 1. So it's going to assign 7. It's going to assign 7 to the next element over. And then j decrements by 1 to become 0. So now we check again. Is j -1? Well, it's not. And is the key bigger than the element at index j? Well, index j element contains 3 because j is 0, so 3. 5 is in fact bigger, so we stop the inner loop right away. So now once we exit inner loop, what's going to happen next? Well, we're going to assign the key into j plus 1. So j is 0, so j plus 1 is going to be sort of this element right there. and the key will be assigned over here. So we simply moved 7 over by 1 to the right to make room for the 5 to be inserted between 3 and 7. So now, after we're done with this, our new list looks like this. So we have 3, 5, 7, and then 2, 6, 4, 1, 8. And now these 3 elements are part of our sorted list. So we're not quite done just yet, but we definitely, from the last step, we had 2 elements. Now the green box has 3 elements. So we are getting, we're getting there. We're not there quite yet, but we are getting there. So now I is going to contain the value 3, because I increments by 1. J will contain, well, we're going to set J to be I minus 1, so J will be set to 2. And the key is going to be the element at index I. So I is 3, so 0, 1, 2, 3. So this element 2 is going to be the value at index I, or 3. So key is going to be the value 2, which is physically the element right after that green box. That's going to be your key, essentially. So let's go ahead and run the inner loop once again. So we first check, is J negative 1? It's not. And is the key larger than the element at index J? Well, it's not, because J is index 2, which is 7, and key is not bigger than 7. So we're going to have to take the element at index J and assign it to element J plus 1. So 7 gets moved over to the right by 1. We decrement J by 1 afterwards, and then we do the same exact process. We check, is J negative 1? Well, it's not. And then, well, is the key bigger than the element at index J? Well, index J contains the value 5. The key being 2 is not bigger than 5, so we have to move the 5 over by 1 to the right. Decrement J by 1. Now J is going to be 0. All right. So is J negative 1? Well, it's not. And is the key value 2 bigger than the element at index J? So index J contains the value 3, and the key, which is 2, is not bigger than 3, so we have to move the 3 over by 1 to the right, like that. And then decrement J again by 1, and now is J negative 1? It is. So we're done. Inner loop portion is finished. So after we finish the inner loop, the next step is to simply assign the key into element J plus 1. Let's look at the code for a second. Right there. After we finish in a loop, set the key equal to element at J plus 1. Okay, so J plus 1 would be 0. We assign the key right over there. So we simply had to move 7 over, 5 over, 3 over to make room for the 2 to be inserted between, or inserted before all of those, because in this case, the key value is smaller than every single element, so everything had to shift over by 1 to make room for the 2 to be inserted into this list. So let's go ahead and rewrite this now. So 2, 3, 5, 7. Then we have 6, 4, 1, 8. Okay. So now the green box is a little larger than before, again, by 1 element. So, we are getting there. It takes time, but, it's going to eventually get there. It'll eventually have the whole entire array will be one big green box, but until then, though, we have to keep on doing this. Okay, so now I is going to be 4, because after we finish one iteration, I increments by 1 to make it 4. So let me make sure, so 0, 1, 2, 3, 4, perfect. Then we set J equal to I minus 1, or 3. And the key value is going to simply be the element at index I. I is 4, so index I contains 6. So we store 6 into the key. We're going to try to find where can 6 possibly go. Now looking at this, looks like 6 goes between 5 and 7. But let's go ahead and go through this entire code. So now we have to run the inner loop. So J is 3, which contains the value 7. So we check, is the key, well, first of all, we check, is j negative 1? It's not. Okay, then is the key larger than the element at index j? And it's not. So you have to shift the 7 over by 1 to the right. Decrement j by 1 to make it 2. So we see here, okay, j is not negative 1. But we check, is the key bigger than the element at index 2, or index j? And index j contains the value 5. The key is in fact bigger, so inner loop can stop right there. So after we finish inner loop portion, we're going to assign the key into position j plus 1. So 6 will be assigned right there. So you have to move 7 over by 1 to the right to make room for 6 to go between 5 and 7. Not very hard to conceptually understand this algorithm. Let's go ahead and just go through all this. So 2, 3, 5, 6, and 7. Then we have 4, 1, 8 at the end. So this part of our array is sorted. So I is now going to contain the value 5 because it increments by 1 after we finish iteration of the loop. So from element 0 to I minus 1 is sorted. Well, I is 5, so from 0 to 4, 0, 1, 2, 3, 4 is sorted. So the proof of this algorithm that works is pretty simple. Maybe I can try to do a loop invariant later on to show that it works. But anyway, for right now, let's go ahead and just stick with this. So I is 5. So then j is going to be set to I minus 1, or 4. And then the key value is going to be the element at index I, or in this case, I contains the value 5, so index 5 contains 4, which is that element right after that green box. So now we have to run the inner loop once again, because we have to do this step all over again, because we don't have the entire list sorted just yet. So now we check. Is j negative 1? Well, it's not. Is the key value larger than the element at index j? So index j contains the value 7, and the key is not bigger than that. So we move the 7 over by 1, decrement this counter by 1 to make it 3. We check again. Is j negative 1? Well, it's definitely not negative 1. So then we can go ahead and just sort of slide, because I guess, what am I talking about? So, okay, so you first check j is negative 1, it's not negative 1. Then we check if the key is larger than element at index j. So index j is at element 3, index 3 element, which is going to be 6, and the key is not bigger than element 3 or 6. So we slide a 6 over by 1, decrement j by 1. Okay, I think that made no sense a second ago. So now, after that is done, we check j once again. Is it negative 1? It's not negative 1. Then we check, okay, is the key bigger than the element at index j, or 2? Index 2 contains 5. The key is not bigger than 5, so we have to slide the 5 over. Decrement j by 1 to make j 1 now. So it's not negative 1, so we can't stop right there. Then we check. Is the key bigger than the element at index j, or 1? And in this case, it is, because index 1 contains 3, and the key is 4, so we're done. The inner loop portion had to move the 7, 6, and 5 over to make room for 4 to go between 3 and 5. So now that we finished the inner loop portion, we're going to assign the key into position j plus 1, so index 1 plus 1 is 2. We assign 4 into index 2. So now 4 is in its correct position for this list right here, for the sorted list. Let's go ahead and copy the list over here. So 2, 2, 3, 4, 5, 6, 7. That's going to be our sorted list. And we still have elements 1 and 8 left. So this is going to be our sorted list. We're not done yet because I does not equal n, which means that once I equals n, then we can conclude it's sorted. That's sort of the loop invariant for this algorithm, actually. As I increments, we keep having a larger sorted list. So we have the we use the definition of a loop invariant that from 0 to I minus 1 is always sorted. So if we go with that rule, as I becomes n, then elements from 0 to n minus 1 will be sorted, so it's sorted. So that's kind of the proof that insertion sort actually works. So I'm not going to really, formally prove that, but I kind of did in a way right there. So now I will be 0, 1, 2, 3, 4, 5, 6. So I is going to be 6 now. J is going to be set to I minus 1, or in this case 5. And the key is going to be that element right after that green part. So element index 6 contains 1. The key will be 1. So let's go ahead and run this inner loop. We first check, is j negative 1? It's not. Is the key bigger than the element at index j? It's also not the case. So the 7 moves over to the right. Decrement j by 1. We check, j is not negative 1. And is the key bigger than the element at index j, or 4? So index 4, which is 0, 1, 2, 3, 4, contains 6. And the key, which is 1, is not bigger than 6. So you have to move the 6 over by 1. Decrement j by 1. Then we check, is j negative 1? It's not negative 1. And is the key larger than element at index j? It's not, because index j contains the value 5, and the key is not bigger. 1 is not bigger than 5, so we have to move the 5 over. Decrement j by 1. And once again, we check, j is not negative 1, and we see that, well, is the key bigger than the element at index j? So index j is going to be 4. So is the key bigger than 4? It's not. So the 4 gets assigned to the next element over. Decrement j by 1. We check, j is not negative 1 once again, and the key value is not going to be bigger than the element at index 1. So we're going to move that element over by 1 to the right, to assign 3 over there. Set j to be 0, decremented by 1. We check, is j negative 1? It's not. And is the key larger than the element at index j, which is not. Index j contains 2, so key of 1 is not bigger than 2, so we assign 2 to the next element over, and then j becomes negative 1, and then we stop. So worst case scenario, in this situation, we had to move everything over by 1 because the element that came after the green box, happened to be the smallest element among our sorted list. So we had to move everything over by 1 to make room for the smallest element to be inserted to the very front of this sorted list. So after we're done with inner loop, we just assign the key to the element at index j plus 1. The j is negative 1 plus 1 is 0. We assign the key, which is 1, into index 0. So now we have a larger list than we had before. So let's go ahead and copy this over here. We have one more step left. So 1, 2, 3, 4, 5, 6, 7, and then 8 is already sorted, but insertion sort has to go through one more step to really be able to conclude that it's sorted. You can't really, right now you can tell it's sorted because we looked at the next element after the green box, but the algorithm itself doesn't know the element after. It has to first check the element before we really can know for sure it's sorted. Oops. So I, in this case, so 0, 1, 2, 3, 4, 5, 6, 7. J will be 6. And the key is going to be 8, the element at index I. So let's go ahead and run the inner loop. We check, j is not negative 1. Is the key element bigger than the element at index j? And yes, it is, because in this case, j contains 6, and that element 6 contains the value 7, and the key of 8 is bigger than 7, so we're done. That was a very simple example of the inner loop. So afterward, we have to assign the key into j plus 1. So we're going to assign 8 with 8. Didn't really do anything, but that's what the code does. We assign j plus 1, so index 7, we assign the key right there. I mean, actually, if you had Insertion Sort on a linked list, it would be really quick. All you have to do is have a pointer that would just, let's say, for example, and let's say in the above example, let's just take a look. Let's look at for we tried to have one. You have a pointer that moves to every node. Once we find where it has to go, we just have to just sort of take this pointer and just sort of take this node and put it between. So let's say, for example, maybe a better example would be above. Maybe let's say for 4. Okay, so we have 2, 3, 5, 6, 7. So you find the index of, find the node that contains a smaller element. So you have to simply take the node 4 and just sort of insert it between 2. You have to actually shift them. You just sort of take that node and reassign the next and previous pointers and so forth to move that 4 in front of 3 and between let's say 5. Let's see, hold on, between 3 and 5. I'm sorry. So you have to just sort of, it's sort of easy to do. It'd be very simple actually because you just move that kind of like pointer over. Once you find a spot, we just kind of take the two nodes and move them, which is a simple pointer reassignment to sort of insert that in between those two nodes, if that makes any sense. Yeah, so anyway, after this is done, we have our entire list as one big list. So 1, 2, make sure I get this correct. 1, 2, 3, 3, 4, 5, 6, 7, 8. We have one big sorted list at the end. So the proof that this works is really just we have sort of our statement that from element 0 to I-1 is always going to be sorted because we always, the interlude portion always makes room for a new element to be inserted between any two values. So we're always going to get one bigger sorted list. And if you keep doing this n-1 number of times, eventually I will equal n. So then from 0 to I-1 will be sorted, which implies one sorted array. That's the proof that this is going to work. That this does in fact sort the array. There's your kind of very not very formal proof right there. Well, actually, the actual proof is actually that, except to use much more formal words than what I just said. But that's really the proof for this. But anyway, that's going to be insertion sort. So for the homework, I'm trying to see if I can incorporate this into an exam as well, but it's kind of challenging for an online exam to do this, but I guess for homework, we'll say for right now, I'm going to zoom out over here. I'll just sort of put this here. So for the homework, you want to essentially show me this. You want to first show me, I guess, each of these parts is one iteration of the outer loop. So I guess you want to, show me this. That's your first step. Then show me this. To show these pictures. So for the homework assignment, which I'll give you, which will be a written assignment coming up, which is kind of, you're probably thinking, thank God, because no coding for right now. You have to trace this algorithm on a list, and you have to really show these arrays, and of course the last array, which is right there. So you want to show each of these pictures, basically. That's sort of the, so for the homework assignment on Insertion Sort, which I'll give you guys next week, don't just, copy and paste the code online and give me that as the answer. No, actually trace the actual algorithm on this list. So do exactly the same steps I did right here in class, but obviously for the homework it'd be a different list, but I can't imagine this being a stressful question on the homework. I mean, it's pretty simple. Just follow this basically, and you're good to go. It's also going to be recorded, this video as well, and notes are posted, so there's no reason why you shouldn't be able to do this on the assignments. So for exam, I normally would give a question like this. We have to trace it out, but I'm not sure on an online exam if it's even possible, because there's many ways you can sort of get this answer, and I'm not going to say more than that, but yeah, so it's probably not possible for an online exam, but for homework assignment, they have to show me your work. You have to, work it out. So I guess it's a pretty fair exercise to give. So, alrighty. So that was Insertion Sort. Any questions on that? That was the actual sort and the actual proof that came along with it. So now let's go over this time complexity analysis. Because once again, we want to, of course, know the runtime of these algorithms. Not really important. It's important to know how they work, but you also want to know what's the runtime. How many steps will it take to run this algorithm? So for every algorithm we're going to be using in class, we're going to have to actually show the runtime for these. So let's go over the worst case scenario, because we always want to know the worst case possible sort of scenario, because that gives us the sort of encapsulates every possible input. So if you know in the worst case it can't get worse than this bound, then we kind of have a good idea of this algorithm. So you want to know the worst case scenario. So in the worst case scenario is that when we actually, so the key value is always the potential, actually I'm going to say it's the min value compared to all the elements in the sorted array. That is the worst case scenario. So if every single time you run the inner loop, you have to move the key all the way to the front every single time, that's the worst case. So yeah, I guess the worst case would be if it's sorted in reverse. You have to go through all those steps like that. So the average case is also where you don't have to move the key all the way to the front. You have to move it all the way to the middle somewhere every single time. That's still going to be pretty bad, but it won't be as bad as the worst case, but it's still going to be asymptotically the same as the worst case scenario. But the reverse sorted is the worst case. So what would happen if this is a scenario? So the number of steps you would have to take, so the amount of steps would be the following. Well, we're going to first do one step, because we only have one element in our sorted list. Next time around, we have to do two steps, because there's two elements in our sorted array. We have to move those two elements over by one to make room for the key. Then next step would take three steps. So next iteration, sorry. So each of you, I'm counting essentially the number of steps done by the inner loop right there. So then it'll take three steps because we have three elements in our sorted list. It takes three steps to move each element over by one to the right to make room for the key to be inserted. Then it will take four steps because now we have four elements in our sorted array. Each one has to move over by one element. There'll be four steps to make room for the key, and so forth. And eventually, plus n minus one number of steps. So this actually, if you didn't already see this, this is actually going to model Gauss's formula. So basically, the number of steps we're going to do, so we can also model this loop structure. It's going to essentially be let me see, j equals 0 to I minus 1. And then we have this outer loop that will run from 0 to n minus 1. So that's going to be sort of the summation, which essentially really is going to be Gauss's formula. So the worst case runtime is going to be O of n squared. I'll box this in red. So that's the runtime for insertion sort. And we care about the worst case because the worst case really kind of, sort of, I don't know, it's going to encapsulate every possible scenario. And for this algorithm, the average case will also be O of n squared because, for example, if you have to move the key a fraction of n number of times, or let's say we have to always move it to the middle. So let's say the key always moves to the middle of the sorted list. It'll take n over 2 steps each time, which will still be relatively n squared number of steps it will take. So as long as the key value has to move a fraction of n number of times over in the sorted list, it will in fact be n squared. Oops. This red dot right there is kind of bothering me. Okay. So yeah, so really this is actually the worst and average case, if you will. So I'll put this here. It's the worst and average case. So average case means most of the time. So usually it's going to be some type of a quadratic growth rate. It might be n squared over 2. It might not be perfectly. It's going to be somewhere in some type of quadratic type growth rate. So as long as the inner loop has to run a fraction of n number of times to insert the key into that sorted list, it will in fact be n squared. Now, I guess we could also go over the best case as well, although it's not really worth thinking too much about this. But let's go over what about the best case scenario. Let's go ahead and think about that. So best case, or I guess you can say maybe a good case, where it's not going to be really, the case above was really the worst case scenario and also modeled the average case as well. So what if the list is already sorted? So if the list is already sorted. Well, if that's the case, then essentially the inner loop runs 0 times every time, basically. So inner loop never runs. So what's going to happen is the outer loop will always run n minus 1 number of times. But the inner loop is going to run 0 times. Let's look at the code for a second and just make sense of this. So in this for loop right there, this will be a constant operation. This is also constant. If the inner loop never runs, this will be just one constant operation as well, if this never runs ever. And then this will also be a constant operation. So you have several operations that are all going to be constant at runtime, and we do this n number of times. So that means it will be O of n if it's already sorted. And the reason why is because the inner loop portion never runs. So the entire body of the for loop will be just one big constant operation, and we run that constant operation n number of times, or actually n minus 1 number of times, which is basically n. So it'll be O of n if it's already sorted, which makes sense. Now, what about the following scenario as well? So we have one other case of insertion sort. So this is sort of like the trivial case, but also we can have another case where insertion sort can also be pretty favorable. So what about the following example? Let's look at this example right here. So I'll have, let's say, so sort of another good case. So we'll have, let's say, 4, 1, 3, 6, 8, 7, 10, 11, 12, 15, 13, and 19. Yeah, this list, it will work. So for some reason, I always wrote these in threes. I don't know why. Maybe there's a reason why I put these always in threes. But in this particular list, we can see the following sort of pattern. So we're given this one list, but let's go ahead and logically sort of look at each of these components one at a time. So this case happens to be 3. It doesn't have to be 3, but 3 is a good sort of number to use. But anyway, in this array, we see here that each of these blocks of size 3, they're not sorted, or actually one of them is, but they're not necessarily sorted. However, you can notice that the block right here that contains 687 is never going to ever have to be in this block, because 413, these are all smaller than 387, or sorry, 687. So none of these elements right here will ever move to this block. And likewise, in this third block over here, none of the elements from this block will ever get inserted into any of these two preceding blocks, and so forth. So this is another sort of nice scenario. So let's suppose, I'll write some notes here. So we can sort of divide the list into n over k, into k sized blocks. Now, this doesn't always happen, but suppose in this case that we actually can sort of see that there are these k-sized blocks. In this case, in this example, k will be 3. So if we have a situation like this, we have these k-sized blocks, and so actually, maybe I shouldn't say divide. That's probably bad. I'm going to rewrite this. So if the list can be, I guess, divided into k-size blocks. That's probably a better way of saying this. If it can be done. If the input is given to us in this type of fashion, where no element from a block will be inserted into any of the preceding blocks. So let's go ahead and analyze at runtime for this. So we're going to have a total. So we have these k-sized blocks. So we have k-sized blocks, and we're going to have n over k amount of blocks. So the runtime to sort each block. So the runtime to sort each block takes, well, it's a summation like this. I equals, I'll say 0 up to k minus 1 I. This will take us roughly k times k minus 1 divided by 2. And k will be a constant of some sort. So we have to make sure that k has to be a constant. So it can't be a fraction of n. Otherwise, this is going to be quadratic still. So k is some constant less than n. Maybe I'll put this above over here. So I'll put this here. K is a constant. That's the idea. K must be a constant, or else this whole entire thing fails. So we have the runtime to sort each block, which will be this. Because really, in this situation, this is going to be really what's going to happen, because it'll sort this block, it will take that many steps. And once we kind of iterate, once I increments to 6, it will take 0 steps, then it will take 1, then it will take 2. So essentially, then once we get to index 10, so forth, it's really going to just sort each block individually because none of the elements from any blocks that are beyond the preceding one will ever move to the left. So really, what happens is each block will get inherently sort of sorted individually. So we can count the number of steps for each of these to take this much. So we have n over k of these blocks. So we have n over k amount of blocks. Each block takes this much time to sort. And if k is some constant less than n, or so it's a much smaller constant, so it's not going to be a fraction of n. It's not a fraction of n, then this will actually, in fact, take O of n time as well. So if we have a scenario like the one above, where the list is given to us in such a way that we have these sort of k-sized logical blocks we can create, and within each block it's not sorted, but they are in fact sorted amongst themselves, the runtime will also be n, or k of n, or k times n, where k is some constant. So as long as k is a small constant, much smaller than n, it will be linear. Now, what if k does equal n? Well, that means it would be n squared. And also, if k equals n, then we have really one big unsorted block, which is the same thing as having one unsorted random list, basically. If k equals 1, then we have a completely sorted list, because that means the first element is sorted amongst, so basically if I say k equals 1, that means this list is already sorted. So as long as k is some constant less than n, and we have these sort of k-sized blocks we can logically create, then the runtime will inherently take linear time. So there are a few good scenarios for insertion sort, but the idea, the real sort of good case scenario, the real idea is, so in the best case, so the best case for insertion sort is when the inner loop runs a constant amount of times. So that's really the best case. And in this situation, even though, so each step so in this case right there, each step, the inner loop will run a constant number of times. Each time the inner loop will run no more than 3 steps for every single time the inner loop runs. In this case, we can see here, no matter where we are in the list, the inner loop will never run more than k number of times, which is why this is also why it's O of n. But I just showed this big example, but really, inner loop can't run more than a constant number of times. If it runs a fraction of n number of times, the inner loop, it's going to be quadratic. And yes, k is 3 in this case, yep. So now the idea is you're wondering, well, what's the runtime for insertion sort then? Because I showed a good case, I showed a bad case, and an average case I didn't really show, but the average case is a very randomized, randomly sort of assigned list. So insertion sort, the runtime is O of n squared. Because we always have to automatically think, well, if we say what's runtime, we think always worst case. Always automatically think worst case. So yes, we have to be pessimistic. I mean, that's what computer science is all about, being pessimistic. And I guess I'm ethnically Hungarian, which makes me even more pessimistic. So pessimism is very good for computer science. Always consider the worst case scenario. If I tell you, what's the runtime if it's already sorted, or if we have, this scenario here, well, then the runtime is O of n, because we have the assumption that the list is sorted, or in this type of nice fashion like this. But if I don't tell you, I just tell you just what's the runtime for insertion sort, you have to consider the worst case, which is O of n squared. And also, the average case will be relatively quadratic as well, because the inner loop portion will always run some fraction of n number of times, typically. So it's going to be really the worst case, really does kind of model the typical case. So it's going to usually be O of n squared, but sometimes, if you're lucky, it can be O of n. But most of the time, though, it's going to be O of n squared. So runtime is O of n squared. If I ask you on a test, well, what if this happens? Well, then it could be O of n if there's a nice scenario, but typically it's n squared. So that's sort of my sort of talk on insertion sort. So we'll go over other sorting algorithms, I guess next week, since we only had only one class this week. So I guess for right now, I'm going to go ahead and stop. So I guess for now, take care, you guys. Stay safe. Thanks for watching. Have an awesome weekend, and I'll see you guys on Monday.